here. I remind you that we have a double feature today, so Dan most of this also correctly. We talk in 3:15. And Scott asked to speak in Hebrew, but I agree with the lecture in English.
Beseder.
Right, yeah.
Okay.
So who will tell us about the determinants of Gaussian?
That's okay. Good. So, all right. Look, it's a pleasure to be here as always. So I want to tell you about some joint work with my student Alex Arkhipov. This is a project about the computational complexity of linear optics. Of sort of what can you do with sort of this type of very sort of rudimentary sort of quantum computer, which is built entirely out of what are called passive optical elements. And the main point of the work is to give evidence that actually this type of machine does not seem to be universal for quantum computation, but nevertheless seems able to do something, to sample from some probability distribution, which is intractable to sample from on a classical computer. Okay, and we're excited about this. Well, initially just purely for complexity reasons, just because we wanted to find some sort of separation between quantum and classical for sampling problems, and it led us to consider this model. But then later we got more excited about it because we realized that it might actually be possible to implement this with much more easily than building a universal quantum computer, and you may even be able to do something interesting with current technology. Okay, so it's a 96-page paper because it's trying to talk to physicists, complexity theorists, mathematicians, so on. So in this talk, I'm just going to focus on sort of the mathematical part of the paper. Okay, and in particular, what I want to focus on are two conjectures that we make about the permanence of matrices of IID Gaussian entries. Okay, and these. And basically, modulo these conjectures, we were able to prove that sort of even approximate classical simulation of our experiment, would imply a collapse of the polynomial hierarchy. Okay, so if you just want to show that exact simulation of the classical experiment is hard, then or of the quantum experiment is hard for a classical computer, then this we can do. This is sort of the easy part. One can show that would imply that in fact, if there were a fast classical algorithm that samples from exactly the same probability distribution as our quantum experiment, then p to the sharp p would equal bpp to the np. Okay, and which for anyone here who's not a complexity theorist, that would be bad. Okay, so the hard problem is to show that even approximate simulation of this sort of quantum experiment that we're talking about would have unlikely consequences for classical complexity theory. And for that, we need these conjectures about the permanence of Gaussian matrices. So that's what I want to tell you about. So I'm going to tell you what these conjectures are. I'm going to tell you sort of how they, I'm going to just sort of sketch how they arise in our work. And then I'm going to talk about what is the partial progress we've been able to make toward proving the conjectures, and what are the barriers, or and what are the obstacles, and so forth. Okay, so so for the whole talk, I'm going to be talking about matrices, say X, which are just n by n matrices of IID Gaussian entries. Okay, so say mean 0, variance 1, over the complex numbers. First of all, because complex numbers are nice. Second of all, because they show up in quantum mechanics, right, in a natural way. So I think that all of the basic issues would be similar if we were to talk about real matrices, or even many issues would be the same if we were to forget about the Gaussian distribution and talk about Bernoulli random matrices, for example. Okay, but I'm going to focus on Gaussian matrices for two reasons. First of all, just that they're in many ways the nicest ones mathematically. Okay, so our conjectures should only be easier, not harder. In dealing with the Gaussian ensemble, we think. But the second reason is that they show up naturally in our context. So basically, our experiment involves sort of applying a Haar random unitary matrix. Okay, so that, which and then the amplitudes for given outcomes of this experiment are given by the permanence of various submatrices of this Haar random unitary matrix. Okay, so now the probability of some outcome, of course, is just the squared absolute value of the amplitude. Okay, so basically what we get to do is we get to sample from a probability distribution in which the probabilities have the form absolute value of permanent of A squared, where A is some submatrix, let's say, of a Haar random unitary matrix, say an M by M one. Okay, so now the question is, what does a submatrix of a Haar random unitary matrix look like? Well, if the submatrix is small enough, then it's easy to see that it just looks like a matrix of IID Gaussian entries, right? So certainly any individual entry of a random, say, orthogonal or unitary matrix will have a Gaussian close to a Gaussian distribution. Okay, and then if you have a small enough submatrix, then you don't really see the orthogonality constraint. Okay, and so then the entries will be close to independent. Okay, this itself, this is like an 8-page proof, that indeed this is the case. But this is something that we do, in the paper. Fine. So this is the reason why IID Gaussian matrices arise in our application. Swastik.
What is a complex Gaussian?
Oh, just the real and imaginary parts are independently Gaussian, each with a variance of a half. Okay. Good. Okay, so yeah, yeah.
Is to show that the permanents are close enough.
No. That has nothing to do with permanence. That's actually just saying that if we take a Haar random, say M by M unitary matrix U, and now we look at some. So I'll say this is Haar random. Okay, just a random unitary matrix. And now we look at an n by n fixed, let's say the top left submatrix of that. And if n is less than some bound, like let's say m to the 1 over 6, okay, then A is close in. Well, in fact, it just A is close in variation distance, which implies that the permanent must be close, right? Because, because you can't even, there's no function of the matrix that will distinguish it from an IID Gaussian matrix, right? So, okay, so close in variation distance. In fact, even the probabilities are multiplicatively close, even at least in one direction. There's a multiplicative bound. Yeah? That just means sort of random from the natural, measure over all the unitary matrices. Okay, so just pick the first row as a random unit vector in C to the n. Pick the second row as a random vector orthogonal to the first one, and so on. Okay, it's just it's the unique invariant measure over the. Yeah, good.
A is a fixed submatrix rather than a randomly chosen.
Yeah, it doesn't have to be randomly chosen. It can be the top left one. Okay, could be, so. Okay, good. So, all right. So this was just why do Gaussian matrices show up for us? Okay, they naturally arise submatrices of unitaries. Okay, now what's the permanent? It's this very interesting function here. Okay, why does the permanent show up in our application? Well, there's a truly amazing fact, which I first learned about 10 years ago, actually in a talk that Avi Vigderson gave here in Princeton. And it's that there are these two basic types of particle in physics, bosons and fermions, right? And fermions are like matter particles, like electrons, quarks. Bosons are like the photons, for example, or the other force-carrying particles. And the amazing fact is that if you have, let's say, n identical fermions, and you want to know the amplitude for them to transition from one state to some other state, you have to take the determinant of an n by n matrix of the transition amplitudes for the individual particles. Okay, and this is basically because, look, the particles are identical, so there are n factorial ways that they could be rearranged, right? And for each one, each of those possibilities contributes an amplitude, which is a product of individual amplitudes. So you get but then with fermions, there's also, if you swap to identical fermions, you get a -1. Okay. So it gives you exactly the determinant function. Okay, with bosons, it's exactly the same rule, except that there's no -1 when you swap, and therefore transition amplitudes for identical. So for fermions, you get the amplitudes are determinants. For bosons, the amplitudes are permanents. Okay, and Avi, remarked that he doesn't really understand particle physics too well, but one thing he can say for sure is that he thinks the bosons got the harder job between the two. So so indeed sort of you could view what our work is doing as sort of formalizing Avi's joke in some sense, right? That
to continue that joke. So, but people do calculations about bosons, right?
Absolutely, they do, but.
Approximations somehow low energy or something?
I mean, there are all sorts of regimes where, quantum physics, reduces to classical, right, and where you can actually calculate things. So, yeah, I mean, okay, so if you want to compute the ground state of, of some bosonic system, that ironically is easier than computing the ground state of a fermionic system, because with bosons, you have all plus signs, and with fermions you also get minus signs, and there the minus signs make things harder. Okay, something physicists call the sign problem. In our context, bosons are the much harder system to simulate than fermions, and it's exactly because of this correspondence, because the boson amplitudes are this very hard function, the fermion amplitudes are this easy function. Okay, so here the minus signs make things easier computationally. So so of course the whole thing we have to do is design an experiment so that we do get a hard problem, right? If we and then the whole thing we want to argue is that if there were a fast classical algorithm to simulate our experiment, then that would have interesting complexity consequences, right? So if you change our experiment in various ways, that may no longer be the case. Okay, so in fact this course this goes very far. I mean, there was a very beautiful result of Les Valiant from 2002, where he considered what he called match-gate computations. Okay, later it turned out that what Valiant had been talking about, although he hadn't realized it, was just systems of non-interacting identical fermions. Okay, basically he'd rediscovered the fermion. Okay, but this what he showed is that this was a very interesting class of quantum computations which could be simulated in polynomial time on a classical computer. Okay, and and ultimately you could say the reason for that is that the determinant is in P. Okay, we're considering the analogous an experiment very much analogous to Valiant's, but with photons, which are bosons, okay, instead of the fermions, and then the amplitudes will be given by permanents, which is what we want, because we want a hard problem.
I mean, in statistical physics, there are also some other examples where you have like the Potts model or whatever. So you have some type polynomials which are also hard to compute. So this would also be an example of something that I mean, it's a physical system that still is hard to
So okay, so there can be examples where, you know, computing the ground state, and even in classical physics, right? There are examples where computing the ground state, let's say, is an NP-hard problem, right? But if that's the case, then we don't expect that nature, herself will find exactly the ground state, right? Because, you know, we don't think that nature is, you know, solving the NP-hard problem, right? But so then you could say that then arguably the question becomes less relevant, right? So we're trying to do is, you know, an actual experiment, right, where where the real answer that's predicted by quantum mechanics, right, therefore you'll actually observe is something which is, you know, would be hard to produce classically. Okay, yeah.
But no, this question was
Yeah.
Computing the Tutt polynomial, which
Is also
it's also there's
Mhm.
some values where you can
Right.
compute it on
Yeah.
a
Yeah.
like a quantum polynomial time algorithm.
Yeah. That this is true.
So then are those points where you can compute it in quantum polynomial time also in the polynomial hierarchy to compute?
Oh, well, okay. Well, it's known that actually approximating the Tutt polynomial at these points is actually a BQP complete problem. Okay, so it actually characterizes quantum computation. So it's, you know, so it just takes us back to the old question of how does BQP relate to the polynomial hierarchy, which, you know, a number of us have been thinking about lately. That's a whole nother talk. But all right, so okay, and now, you know, just one crucial point is that, you know, we're talking here about permanence of general matrices of complex numbers, okay, not of non-negative matrices. Okay, so, you know, the permanent of a non-negative matrix may be, you know, hard to compute exactly, but there's a celebrated algorithm due to Jerram, Sinclair, and Vigoda that lets you approximate permanence of non-negative matrices in polynomial time, okay, using Markov chain Monte Carlo. Okay, so for our purposes, we think of the permanent of a non-negative matrix as being easy. Okay, but, you know, with permanence of general matrices, the situation is completely different. There you have massive cancellations, and there, you know, we don't know of any, you know, efficient approximation algorithm, and that's going to be a crucial point for us. Okay, all right. So without further ado, what are the conjectures that I want to talk about? So okay, the first one is simply, you know, an anti-concentration conjecture for the permanence of Gaussian random matrices. Okay, and this is, you know, something very, very simple. I think it's very interesting, even independently of our application. You know, but it's one thing that would help us a lot, and which sort of maybe surprisingly is already not known. Is already, asking for more than what the best current results can provide. Okay, so what does this say? Okay, so I'll just write n to a shorthand for N001C, right? Of the IID, that's the Gaussian distribution, mean zero variance 1. Okay, so here's a formal statement. Basically, all it's saying, so you look at the permanent of a matrix X of IID Gaussians. Okay, and you know, what can we say about its distribution? All right, well, certainly, you know, the mean is 0 by symmetry. Okay, the second moment is also very easy to calculate. So the variance is just n factorial, right? Because you get these you know, for each generalized diagonal, right? Each one contributes 1 to the variance, and then two different ones they just cancel out, and they contribute nothing. Okay, so the standard deviation is square root of n factorial. So basically, if you look at the permanent of a Gaussian matrix, you expect its permanent to be something like square root n factorial in absolute value, right? You have these n factorial terms, they cancel each other out in some pseudo-random way, right? And what's left over, the residue that's left over, you expect to be about square root of n factorial. Okay, and now the question is, is that really the case? Okay, and now the problem is, could it be that the permanent is just almost always 0, or just extremely close to 0, and then only occasionally it becomes enormous? Okay, that would be a very bad situation for us. Okay, if that were the case. And so basically what this conjecture says is that situation doesn't happen. Okay, and that more formally, it says that the probability that the permanent is less than the standard deviation divided by some polynomial factor is itself at most 1 over polynomial. Okay, that's intuitively what it says. Yeah, Zev. Good question. I think that actually it's not true. It's known not to be true for arbitrary polynomials. So maybe Shachar just had a paper about this. Maybe he can. Oh, is he still here? Or no? Yeah. Oh, hey, yeah.
It should hold, right? If you just take like 1 Gaussian to the power of n.
Yeah, exactly. Yeah.
Something like an exponential dependence on it.
Yeah. So yeah, no, I think it's not true for arbitrary polynomials, but. Mm-hmm. Okay. So put in some more assumptions. Then I don't know. Maybe there's maybe it holds more broadly than just for the permanent.
Well, for general polynomial, you would put the standard deviation still.
Yeah.
You are going to replace a
Uh-huh.
square root n factorial by
Right.
the standard deviation.
Yeah. So
How about for the determinant?
okay. So that was actually okay. Yes. So what I was just about. So thank you, Russell. So what I was just about to say. So first thing we did is all right. Of course we did the numerics. Here's, it sort of looks like this. So it's certainly more concentrated than a Gaussian would be. So this is like these are let's say n factorial and 1/2 n factorial. This is for like 6 by 6 matrices, I think, but we went up to 10 by 10. So yeah, this is the squared. So it looks like this, and then here's for the determinant. Okay, so they look kind of similar. Actually, for the permanent, it actually looks better than for the determinant in terms of anti-concentration. Okay, so numerically, certainly, if we had been physicists, we would have stopped here and said, this thing is true. But all right, but of course we want to prove this. So what is it that we can prove regarding this conjecture? And that leads me just to Russell's question: what about the determinant? So indeed we can prove it in the case of the determinant. Okay, so where should I?
But you had to do it?
Yeah. We were able to use a result from a paper by Costello and Vu, but then which characterizes what the distribution looks like. But then we had to prove yeah. So yeah. Yeah. Yeah, well, I mean, one thing we found, so of course a lot is known about these questions in the random matrix theory literature, but it's almost never sort of exactly what's needed for a complexity application, because it's about it converges in distribution to to this distribution, but then you want to know for some finite value of n, what is the probability of a bad thing happening, and they never directly tell you that, so you have to sort of figure that out. So okay, so fine. So what can we show? Okay. So so this proves the analogous statement with the determinant in place of the permanent. I've sort of put the I've written it a little bit differently, but.
Do you need this generality, or could you just plug in beta equals 1?
We could, so plug in. I mean, this is the strongest thing we know, but you could even plug in beta equals 1, in which case you'd get, all right, this is at most n to the 3/8 times epsilon, right? Okay. This basically says you can even make beta larger. You can make it anything less than 2. Whether you can make it exactly 2, we don't know. So you can't make it more than 2. No, there's not. I mean, this epsilon, the n is the bad part, and the epsilon is the good part that that kills off the n. So, yeah. Oh. Let's see. Well, okay. Okay. All right. And okay. Good.
Beta bigger than 1.
Yeah.
I think the probability, I mean, if you think of n as a constant, the probability of it being in an interval with epsilon is like epsilon squared.
Well, that's what we hope is true. We can get beta arbitrarily close to 2, right?
Or let's say
Yeah, but remember that the per of x is a complex number, right? So that's where the squared is coming from, because you consider this region, right? This region in the complex plane around 0. So, all right, good. You got it? Good. So, yeah, or determinant, excuse me. All right, so I can say a little bit about how we prove this. So, so the crucial lemma is, so it's a very simple, known fact. One place you can find it is in a paper of Costello and Vu. And it says that if you look at a Gaussian matrix X, look at its absolute value of determinant squared, it has the same distribution. As this, where the gamma ij's are IID Gaussians. Okay, so it looks like basically a product of 1 Gaussian squared times 2 Gaussian squareds times 3 Gaussian squareds, and so on up to n, where all of these Gaussians are mean 0, variance 1, and all independent of each other. Okay. Or to put it differently, so a sum of the squares of k independent Gaussians is called a chi-squared random variable with k degrees of freedom. Okay, so it's just a product from all I equals 1 to n of a chi-squared variable with I degrees of freedom. Okay, and all of them independent. Okay, so why does the determinant have this distribution? Well, it's basically because of the rotational invariance of the determinant, together with the rotational invariance of the Gaussian distribution. Okay, so so what you can do is consider your matrix, and now we know that sort of performing unitary transformations, on the set of rows or the set of columns is not going to affect the determinant, and so we can use those to diagonalize the matrix. Okay, and then once we diagonalize it, then the determinant is just the product of the of the entries along the main diagonal, right? And so we do that, and you diagonalize the first row, and then what's the absolute value of this first thing? Well, it's just the norm of this first row, right? Which is just a chi-squared variable of n degrees of freedom, right? It's just square root of or the square root of that, square root of the of all these things, where all these guys are IID Gaussians, right? And then you diagonalize the second row, and that gives you a chi-squared with n minus 1 degrees of freedom, and then and so on, and then you're just taking the product of all these entries along the main diagonal. Okay, so you can easily confirm this fact. Then we want to, using this fact, we want to prove an anti-concentration bound. To do that, we use the fact that there's an explicit form for what is the PDF of a chi-squared random variable in terms of the gamma function. Okay, so then we need to do a few pages of integrals involving the asymptotic behavior of the gamma function. And actually, I was very excited. This was the first time in my research career that the Euler-Mascheroni constant actually came, the 0.577 actually came up, played an important role. But basically, you have to look at the at this thing, and what we do is, okay, we use the fact that because this is a product of independent chi-squared variables, ultimately we can compute all of its moments, okay, and even the fractional moments and even the inverse moments. Yeah.
Do you really have to do all that work to get some bound, or just to get the type bound?
Well, to get a bound that's as tight as we need, this was the simplest way that we could say. If there's a simpler one, then I'll be happy to hear it.
Okay.
Yeah. So I mean, basically, we want to compute the inverse moments, and then we bound that. So what we prove is that. I'm sorry. Okay. Okay, so here's the theorem we proved to calculate the moments of the determinant. Okay, basically, you're going to get, if you look at determinant to the 2 alpha power, it's going to look like n factorial to the alpha power, but then, times some additional term, and that's really what we're interested in. Okay, and what the theorem says is that additional factor looks like n to the, some polynomial in alpha, n to the actually alpha times alpha minus 1 over 2, times some constant depending on alpha. Okay, so this is what comes out at the end of all this gamma function calculation.
So if you have some product of independent things with bounded PDFs, is it
Yeah.
easy?
Well, I mean, we do it, right? I mean, yeah.
You just do it for,
Yeah.
it's generalized to anything that has a bounded PDF. Because except for chi-square random variables with 1 degree of freedom,
Yeah.
quite nice, right? That would be bounded.
Yeah. Well, I mean, we're certainly, using the, specific facts about these PDFs. For other PDFs, the statement would be false, I think. I mean,
Other bounded guys with bounded.
for other bounded PDFs,
Like, are you really using,
I think so, yeah.
what else are you using? Like exponential theorem?
Well, we're let's see. So okay, so you're saying maybe you could just use what the. I mean we're calculating the moments, right? We're using the fact that the moments behave well. So you're saying, could there be PDFs for which the moments, could there be products of independent variables with bounded PDFs for which the moments behave badly, for which the inverse moments, let's say, behave badly? I don't know. That's a good question. We can talk about it later. Okay. All right. So this was one thing that we could do. The second thing that you'll notice that this solution for the this anti-concentration bound for the permanent for the determinant crucially relied on the the geometric nature of the determinant, right, and the fact that it has this rotational invariance, and we don't see at all how it would generalize to the permanent. Okay.
Can I ask one more question?
Yeah, sure.
Can you, with the permanent conjecture, can you get bound that depends, polynomial in epsilon with a big polynomial, if you allow like a factorial, say, dependence on n?
Oh,
You
that's
can, like, n
that's very
factorial
you probably could. I think you could, and that may even follow from there's a recent result of tau and vu that gives us some bound for the permanent, which is not good enough for us. So that may even follow from their bound. Okay, so all right, so what else can we do? All right, so you might say, all right, in the case of the permanent, well, let's try to calculate its moments. So and we can push that to some degree. We can calculate the fourth moment of the permanent exactly, and that gives us in fact it turns out to be exactly this. Okay, and using that we get actually a weak anti-concentration theorem for the permanent, which says the following. It says for all alpha probability that the permanent of x is greater than or equal to alpha times root n. I guess this is for all alpha less than 1 is at least minus alpha squared divided by n plus 1. Okay, so by using the fourth moment and then together with Cauchy-Schwarz, I think we can get that the permanent has some 1 over n probability, basically, of being large. Okay, but of course that's much weaker than what we wanted. We wanted that it has like a 1 minus 1 over, poly n probability of being large. But yeah.
Did you ask Tao and Vu about this conjecture?
We did. I'm going to get to that. We asked both of them. And, yeah.
Do you feel there's any hope for the other even integer moments?
That's an excellent question. We looked at it. So you might ask, what about the sixth moment, the eighth moment, and so on? Okay.
So use a computer to guess the answer, but maybe it looks
We could. Yeah. Well. No. This might be doable. It's an interesting combinatorics question, which I can now tell you exactly what it is. Okay. So what if we want the 2kth moment of the permanent? Okay. Then we can actually characterize this as expectation. Let's see. Okay, so this is what we get. So let G be a bipartite multigraph with n vertices on each side, and which is k regular. Okay, so so every vertex has degree k. Now we know that any such multigraph can be decomposed into you can think of it as just a union of k perfect matchings. Okay, that's right. And then the question is, how many ways are there to decompose G into k perfect matchings, and and take the expectation of that over all such G. That and I'm sorry, and there's some factor of n factorial to the k here. Okay. Yeah.
So all the ones that are not multigraphs, you know exactly.
Mhm.
I mean, it's the same number for all of them.
Yeah.
Okay.
Mhm.
When k equals 2 to get
Yeah,
that,
exactly.
that is exactly that.
Yep. Yeah. Exactly. So yeah. So this comes.
A union of,
Yep.
G is a random
Yep.
union of cycles.
Yep. Yep. Exactly.
Decomposing G into ordered list of k perfect matching.
Yep.
Like pick.
Yep. Yeah. It's a 2 to the power of the number of cycles. Yep.
The expectation to the number of cycles is n plus 1.
Yep. Exactly. That's exactly it. Thank you, Russell. So okay. So
Similar,
but,
even for K, that's similar to the
Yeah.
computation that comes in those models for random regular graphs.
I see.
So
Okay. Good.
it's,
Good. Good. So.
so you can know the asymptotics of this probably.
Oh, we do know the asymptotics, yeah, but so in fact, what's known about the asymptotics is that for k, okay, so for k equals 2, as I said, we can work it out exactly. You get n plus 1, okay, which we like because and it's because when k equals 2, we just have this union of cycles essentially, okay. But when k is greater than or equal to 3, then there's a phase transition, and there's a completely different behavior, and this m of g goes asymptotically like k over e to the n, okay. And this follows from what's called the van der Waerden conjecture, which was a major conjecture about the permanence of doubly stochastic matrices, which was proved by Igorichev and Flickman in the 80s. And as a consequence of that, you get for k greater than or equal to 3 that actually this quantity grows exponentially with n.
Presumably you need means as well. So when the
Huh?
Waerden is a lower bound, and means
Yeah.
conjecture is an upper bound.
Yeah, that's right. That's right. I think so.
Well,
Yeah. So yeah, putting both of those together, you get this. But then this is the asymptotic behavior. But then we don't know the exact value.
To get the, I mean, to use it,
Yeah.
it's not enough to get the anti-concentration. Like you need to know the.
Well, so
you need to know the exact number.
right. Because these things are exponential, they don't directly imply anything about anti-concentration. If we knew them exactly, then they would determine the distribution. So in principle, they would give what we needed.
But you're saying this k over e to the n, it doesn't help.
Yeah, just knowing that it's k over e to the n, as far as we could see, it doesn't help.
over e to then when you write, you mean for large k, right?
Yeah, that's right. I think even for k equals 3, it's like this. But
It's another exponential probably. I don't think.
oh, you don't think that it's this exactly? Oh, okay.
It's a case root of k.
I see. Okay, it may very well be a different exponential, but I know that for k greater than or equal to 3, it is exponential. Okay. All right. So all right. So I can just tell you the result also of that Tao and Vu proved. So where is it? I probably remember. Okay, good. Oh, all right. I'll use this one. Okay. Okay, so they proved to be like possibly the first sort of really non-trivial anti-concentration bound for the permanent. Okay, but it falls short of what we need in a few respects. Only one of which is really important, I think. So the main respect in which the results fall short is that they're able to upper bound the probability that the permanent of x is at most square root of n factorial divided by some exponential in n. Okay, in their case, n to the epsilon n, their techniques may also let you replace this by c to the n, maybe even c to the root n, but there's still some exponential downstairs here, and whereas we need a polynomial downstairs.
So they're really bounding the log of the
You could say so, yeah, you could say so. Yeah, and now the other differences are, first of all, this is not, upper bound on the probability is 1 over n to the 1/10, let's say, which is not good enough for us, right? And secondly, this is the Bernoulli distribution instead of the Gaussian one. However, those two differences actually cancel each other out. So I had a very nice correspondence with Terry Tao on Math Overflow, and he pointed out that if you were to redo their result with Gaussian matrices instead of Bernoulli ones, I mean, it would only become easier to prove, and he thinks, he's not sure of this, but he thinks that this n to the epsilon n would become 2 to the root n, and that this 1 over n to the 1/10 would become like 1 over polynomial or something. Okay, so then the one remaining problem would be that this either 2 to the n or 2 to the root n would have to become polynomial in n. So that's pretty much where things stand. Now, if you look at the proof of this Tao-Vu result, it's really just sort of going through in this sort of very bare-handed, minor by minor way, right? And just sort of, you can't quite argue. I mean, the main problem, if you knew that all the minors of your n by n matrix behaved independently of one another, right? Then the anti-concentration would be clear. But of course, they're not independent, right? The minors can overlap each other. And so they just use the fact that, okay, if two minors are disjoint, then certainly their permanents are independent, right? And and they get as far as they can just using that fact. Okay, so it's kind of a very bare-handed approach. It's very combinatorial, and I think the hope is that there's some more analytic approach that would avoid the need to go in this minor by minor fashion, because when you do that's when you lose this exponential factor. So.
You think that for Gaussian it should be much easier, right? Because
well, I hope so. I don't. Yeah.
One minor which
Yeah.
is big,
Mm-hmm.
and then you just look at the value of the last Gaussian that multiplies it. Right?
Okay. I don't know. Maybe you're right. I don't know. I mean, all I can say is we tried, and and this dependencies between the minors kept killing us. But I don't know. Maybe. Yeah.
Why does Tao-Vu care about the permanent?
Just for its own sake, they didn't realize that it had a crucial application to quantum optics, but we were happy to inform them of that. So, all right. So, okay. So in the remaining time, let me tell you about sort of the second conjecture, which is maybe I think the more important of the two, but it's also okay. Bye, Shachar. Also the one about which we know less. Okay. Let me first define a computational problem. Okay, so we call this the GPE problem, Gaussian permanent estimation, and this times is just to indicate that we want a multiplicative approximation here. Okay, and what this says is okay. I remember it. Okay, so here's the problem. You're given a matrix of IID Gaussian entries. Now you would like to approximate its permanent to within a multiplicative error of epsilon with probability at least 1 minus delta over the choice of matrix. Okay, and you would like to do so in time which is polynomial in n and 1 over epsilon and 1 over delta. Okay, so in other words, more formally, you could say that the input consists of n and then 1 over epsilon zeros and 1 over delta zeros, and and you want to just do it in polynomial time. Okay, so this is problem, and now. State the conjecture. We call it the permanent of Gaussian's conjecture, or PGC. And it says that this, estimating the permanent of a Gaussian random matrix is a Sharpe-Hard problem. Okay, so the name, of course, is a pun on the UGC, which if you know about, which says that sort of this problem that sort of looks like it just clearly ought to be NP-hard really is NP-hard, and this is saying that something that looks like it clearly ought to be Sharpe-Hard really is Sharpe-Hard.
Wait, it's not
Okay, so
clearly ought to,
well, all right, fine. I'm just what ought to be the case isn't always what is the case, but all I claim is that it ought to be the case.
No, that's why approximating over integers is sigma 2, right?
So no, over non-negative matrices. Yeah, is easy. Okay, well, so intuitively, I think the case of you really have to think of the case of non-negative matrices as a completely different animal, and the reason for that is that first of all, if you've got non-negative terms, then just by Stockmeyer, it's always going to be in BPP to the NP, right? But second of all, in fact, in that case, it's even in BPP because you can use Markov chain Monte Carlo, right? But here, if you've got a complex matrix and you're trying to estimate its permanent, right, then you've got these cancellations between positive and negative terms, and also, of course, positive and negative imaginary terms, right? And what you're trying to estimate is just this tiny exponentially small residue which is left over after all that cancellation. Okay, now not coincidentally, that's exactly the sort of thing that a quantum computer can do, right? Which is why we're talking about this problem in the first place. But the conjecture would be that this is something that is classically hard. Yeah.
So just like the James conjecture, the conjecture as stated is that it's NP-hard.
Yeah.
But
really what we need. Okay, so let's thank you, Russell. So in fact, what all we really need is that this problem, Gaussian permanent estimation, is not in BPP to the NP. Okay, as long as it's not in BPP to the NP, then all the conclusions of our paper follow. Okay, so it being Sharpe-Hard would be one very good way for it to not be in BPP to the NP, right? Assuming that pH is infinite. Okay, but this is conceivably it could fall short of Sharpe-Hard, but still not be in the polynomial hierarchy, and that would be fine for us. Yeah, exactly.
So this 1 minus delta then is with the probability of the algorithm and with the probability inherent in X, right?
Yeah. Well, because the input is random without loss of generality, the algorithm can be deterministic. Right? But fine. Okay, yeah. Say probability 1 minus delta over X. Yeah. Okay. Excuse me?
Can't you replace in your Witcher sufficient form, as you say, of course it's not to consider deterministic algorithm.
Yeah.
So can you say that if it's not in sigma delta 2 or something?
Yeah. I said that, right? I wrote that.
Yeah, okay, sorry.
Okay. Yeah. Okay. All right. So I should say a little about why do we expect, what? Yeah.
is it easy to compute the sign of permanent?
That's an excellent question. And so one of the main technical things we have to do in the paper is show that computing the sign of the permanent of a Gaussian matrix is as hard as computing the permanent itself, assuming the anti-concentration conjecture. Okay, so it's just gonna get to that. And that's about a 10-page proof. It's not intended for anyone to read, but we wrote it. So okay, so good. So I was just going to get to this, but assuming the anti-concentration conjecture, actually we can first of all we can show that it doesn't matter if you have multiplicative or additive approximation, right? Those become equivalent for this problem. And secondly, it doesn't matter if you're talking about the permanent itself or the absolute square of the permanent. Okay, that those two are also the same. Okay, so that's the formal role that the anti-concentration plays in our work. Okay, that it allows us to just base everything on the Sharpe hardness of this I think very natural problem. Okay, which is just estimate the permanent of a Gaussian matrix, rather than the absolute square of the permanent or something weird like that. Okay, so all right, good. So why might we expect this to be true? Well, so there's sort of two main arguments for it, which is first of all, we can verify that all the known approximation algorithms fail to give anything reasonable here. So I already mentioned Durham Sinclair Vigoda certainly doesn't work because it only works for non-negative matrices. So probably the most relevant algorithms for these sorts of problems are those of Leonid Gurvitz. So Gurvitz had a result that says given an arbitrary matrix X, it doesn't have to be non-negative, so he shows how to approximate the permanent of X to an additive error of plus or minus epsilon times spectral norm of X to the nth power by a randomized algorithm, which runs in time O of n squared over epsilon squared. Okay, so what happens if you so basically he gives like an estimator, right, which never exceeds the spectral norm to the nth power, and it's an unbiased estimator. So then you just have to run this estimator 1 over epsilon squared times and take the mean. Okay, so what happens if you try to run this algorithm? Well, if X is a matrix of IID Gaussians, then what is the spectral norm of X? With high probability, it's about 2 times root of n. Okay, this follows from something called the Tracy-Wiedohm law, but fine. This is what it is. Yep. Tracy and Wiedohm prove, and MATLAB verifies that. Yeah. Okay. No. I'm sure that that's correct. So all right. So then we get an approximation by a factor of like epsilon times that. But what we wanted was an approximation which looks like epsilon times square root of n factorial, and this actually exceeds this by an exponential factor. Okay. By a factor of like 2 times root epsilon to the n. So yeah.
Is it? I mean, they're bound on the
Yeah.
approximation for their algorithm, but
Uh-huh.
have you looked at how their algorithm?
Yeah, actually does. I mean, yeah. You can look at there certainly exist matrices like the all ones matrix. I think for which you do get this worst possible behavior. And if you look at their estimator, there seems like you get like these terms that are that really can be much larger certainly than this. So I don't see any reason why that estimator would work in the Gaussian case. We can talk about it later, but can we prove that it doesn't work?
Yeah.
That's actually that's a very good question. We should try to actually prove formally that their estimator doesn't work. I'm pretty confident that it doesn't, but yeah.
On the idea of like giving every element a negative sign, a random sign, and
Yeah.
Or
It's not. Yeah, it's not. It's not the same as the Godsell-Gutman estimator, which actually doesn't work here. Okay. It's what is it? It's but you can use. There's a there's this alternate version of the perm. There's a different way to write the permanent, which lets you compute it not in n factorial time, but now in like 2 to the n times n squared time, right? It's called Reiser's algorithm, right? And so basically, it's you run in Reiser's algorithm, rewrites the permanent as the expectation over like over a string of n bits, right? Over like a string of n plus ones and minus ones. So it's basically just you run Reiser's algorithm on some random plus ones and minus ones. Okay, you observe that the Reiser's algorithm constitutes an estimator that never exceeds the spectral norm of the matrix, and then okay, fine. So this was one known approximation algorithms fail. Now the second, maybe the main piece of the main reason to believe that this that maybe this permanent of Gaussian conjecture is true is that if you consider the analogous statement for the permanent, of a matrix of finite field entries, then certainly it's true. Okay, that so there's this famous result, I think originally from Lipton and then since improved by a whole bunch of people, that says that over a finite field, to compute the permanent of a random matrix is just as hard as to compute the permanent in the worst case. Yeah, well, there is no, there is no such thing. But, but my intuition is if you take a finite field statement and you change it, now you switch to the reals or Gaussians, then you should also allow for some approximation. But fine.
How about
Yeah.
the exact?
Yep, over the Gaussian distribution. So this is indeed a question which we considered and which we answered. So, okay, so one thing that we can prove, good. Okay, so one theorem which we prove in the paper is that okay, so this is something we can show. That if you want to exactly compute the permanent of some complex matrix X, and you want to do it with high probability over X chosen from a Gaussian measure, then this is sharp P-hard. This is a sharp P-hard problem. Okay, and we can show it for 3/4 plus delta. This ought to even be true for half plus delta, probably even for 1 over polynomial in n. Okay, so yeah.
So what exactly do you mean by exactly computing?
Okay, yeah. So all right. So what when I say exactly, really I mean really closely. Okay, I mean. Yeah. So truncate the entries, represent them to n bits of precision, and then say you can compute the permanent to exponential precision. Okay, so precision of like I think any exponential precision would actually suffice for us. So say to n bits of precision, you can compute the permanent. Okay. Not that I know of, no. Because over finite fields, there's no notion even of the mean, right? So yeah.
How about random 1 minus 1 matrices? Is that?
Good. So yeah. So one could certainly look at the analogous conjecture there, and there I'm not sure. I'm not sure if the analogous statement would hold there. So so here what we use is we sort of all right, so if you think of the proof of Lipton, of the random self-reducibility of the permanent, how does it work? Well, it uses the fact that the permanent is a low-degree polynomial, basically, and that low degree polynomials are excellent error correcting codes. Okay, so what you can do is, assuming that you can compute the permanent of most matrices, then, here's your target matrix X. Now just pick like some, let's say a random line, in FP to the n times n that goes through X. And now you have some other sample matrices. You compute the permanence of the sample matrices using your algorithm, and then you just fit a low degree univariate polynomial through them, and then you evaluate that polynomial at X. Right? It's a very, simple idea. So what basically we try to do, we try to do the same thing in the Gaussian case. And what we find is that if for these sample matrices you could exactly compute their permanence, okay, then the same idea works. Okay, so we can use the fact that so you don't quite have you can't have it be that all of these matrices that all of these points will be Gaussian samples, right? Because the Gaussian measure simply doesn't behave that way. But what we can use is the fact that the Gaussian distribution has a very good autocorrelation. Okay, so you shift it by a little bit, and and you get a distribution which is close to the one you started with. Okay, and using that, what we can do is we can say, all right, let's say here's your target matrix X. So now just pick a random line. Now this is a line in C to the n times n that passes through X. And now we can have one other point along this line. Let's call it Y, which will be Y1, which will be a Gaussian random point. All right, and now we want some more points that are in order to do our interpolation. So we'll just pick a whole bunch of other points that are all very close to Y1. Okay, and now each of these points individually, by the the union bound plus the autocorrelation of the Gaussian measure, they'll all be very close to Gaussian. Okay, so with high probability, we can exactly compute the permanence of all of these. And then, because we got the permanent very, very exactly, we can then do the interpolation, and it works all the way over to X.
Okay. Can you fill in some more details here?
Yes, I can.
Good.
Yeah.
I don't even see how to get that first Y1.
Okay. All right. All right. So so how does it work? So let X be a target matrix, I'll say. So
Gaussian, are you using this the regular kind of?
no. So it's nothing that complicated. Right.
You don't know fancy.
Right. So let X be a matrix of of complex numbers, which is worst case, and whose permanent we want to compute. Okay, then we will show how to compute it. Assuming we can compute the permanence of most Gaussian matrices. Okay, so how do we do it? Well, first just choose a matrix Y from the Gaussian measure. Okay, just choose it. Okay, and now we'll consider permanent of t times x plus 1 minus t times y. Okay, and this will be a univariate polynomial of degree n in t. Okay, and now what we're going to do is we're going to evaluate this polynomial at a whole bunch of points which are close to 0. Okay, so that it's mostly so in other words, we're going to evaluate the permanent of a whole bunch of matrices that are all close to y. Okay, now because of the autocorrelation of the Gaussian measure, all of those matrices will actually be drawn from something very close to the Gaussian distribution. Okay. So here we'll use the fact that we'll assume that the entries of xij are bounded. Okay.
You can even assume X is a 0, 1 matrix.
Yeah, exactly. We can. That's already a Sharpie complete problem. Exactly. Okay. So anything sufficiently close to y is actually very close to a Gaussian matrix. Okay. And so so then by our assumption we can, for most of those, we can compute the permanent. Okay, and then we get a bunch of values of a polynomial. Let's say 3/4 of which are correct, or but when they're correct, they're exactly correct, right?
How small is t again? So for that
Oh, t will be like 1 over poly of n. Okay, 1 over n squared, something like that. Something like that. Yep.
So it's like a perturbation of a Gaussian.
Yeah, exactly. They're all just perturbations of y,
And
just
for
moving.
Statement, is
And the statement is that assuming that we've got the values of p at, let's say 1 over n squared, p of 2 over n squared, up to p of n over n squared, then, using these, we can actually, if we've got 3/4 of these correct, here, maybe I'll make this.
But only approximately.
No. All right, to within exponential precision.
Oh, this is very.
Yeah.
Oh, I see.
Yeah, to within. If we've got 3/4 of these, and the ones that are right to within exponential precision. Okay, then actually we can do extrapolation. We can get p of 1. That's the statement. Okay. Yeah, nothing special about it. It's just it comes up from using the union bound. I'm sure that you could replace it by half plus delta, and then probably even by using Sudan's list decoding, you could even get it down to 1 over poly. But which has been done in the finite field case, but we didn't bother to do it in our case. Yeah.
Decoding is problematic over real.
Oh, really? Okay. Well, maybe not. All right. Well, then let me put it as an interesting open problem. Can this be? Can you put in Sudan's list decoding here to get this down to 1 over?
What you mean by it, but
Yeah. I mean, in any case, it's not something that would be needed for our application. But it's a nice question.
So the algorithm only applies the hypothesis that you have an algorithm for the Gaussian.
Yeah.
So you get this not quite Gaussian matrix.
Yep.
You just round it to the nearest.
No, you can just run directly because the point is that the Gaussian measure has good autocorrelation. Okay, so something which is drawn from a slightly perturbed Gaussian, it actually essentially is drawn from Gaussian with high probability, right? Yeah.
Bigger spacing between these points.
Yeah.
Would it require to have smaller approximation to get correct value?
Yeah. So of course, what we thought about next is so the actual spacing between the points is not what matters, right? But what matters is how close are these points to to the final thing you want to approximate, right? So of course we thought about what if you took points that are spaced out like this? The problem then is that these so certainly if we could if we even had approximate values of the interpolants, then we could of the sample points, then we could just extrapolate and we could get p of 1. But the problem is that these points are not anywhere close to being Gaussian random, right? Because they're too close to this worst case matrix X. Okay, so in fact, this is we can actually show that in some sense this is a fundamental barrier. That sort of you're gonna get one problem or the other one. Okay, and the basic reason for that is that the polynomials as a set of interpolants are a linear set of interpolants. Okay, so if p and q are two possible interpolants, then so is p plus epsilon times q, let's say, right? And we can prove that no class of interpolants that has that property of linearity, can suffice to solve this problem. Yeah.
Yeah. So you're it's a little bit fishy because in some sense you're saying the correctness of all of those points is essentially because they're close to Gaussian is essentially the correctness just about this matrix Y.
Yes. Yeah. It's just a union bound. It's just a union bound.
Yeah.
There's nothing
but
fishy.
you
Yeah.
basically have, right.
Yeah. Okay. Yep.
I mean,
Yep.
It says, but
Yeah.
the union bound is telling you that really the change based on X really didn't matter very much.
Right.
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 So it's a little fishy how you're getting more information out of
Well,
this in some sense. Since
all-
all your bounding is in terms
Yeah.
of the computing things with Y, how
Yeah.
you're getting more
Yeah.
out of this.
Well,
than
well-
determinant
Because
of
it's so
Y.
accurate.
Yeah, right. It's because the approximation is so accurate. As I said, this indeed doesn't work if you only have approximations of the p of x axis. Yeah.
So you're saying if you can exactly compute permanence of Gaussian matrices,
Yep.
you can exactly compute symbolic permanence
Yeah.
of
Of lines through the yeah.
where the matrices where it's Gaussian plus or minus
Yes.
epsilon in each.
Yes.
It
Yes.
has, yeah, it has very little to do with Gaussian. So
You could say, yeah, all we're using about the Gaussian is that it has the autocorrelation that we want. Yep. Yeah. So okay. So the question for the what about approximating? So what this is saying is that the difficulty in proving this PGC conjecture really comes from combining average case with approximation. If you have either one of the two, then we can show Sharpe hardness. Okay. It's only for the combination of the two that there's a question. Now, and for that question, we can prove that some new approach is needed. Okay, in other words, interpolation, using low-degree polynomials is not going to work. You're going to need some other class of interpolants which does not have the property of linearity. This is what we can show. Okay, so those were the conjectures. If, just to recap, if you prove both of these conjectures, then we can give an experiment that seems, feasible or very close to feasible with current technology, such that, which would sample from some probability distribution, in this case a distribution over numbers of photons in a given location, such that if you have a polynomial time classical algorithm that samples from any distribution which is even close in variation distance to the one that the experiment is sampling from, then the polynomial hierarchy collapses. Okay. So that's the goal. Thanks.